On January 28, 2026, NASA announced they had found the oldest galaxy ever confirmed. It's called MOMS 14, and we are seeing it as it looked just 280 million years after the Big Bang. That might sound like a long time, but consider the scale. The universe is 13.8 billion years old. So this galaxy existed when the cosmos was basically a newborn, less than 2% of its current age. To put that in perspective, if you compress the entire history of the universe into a single calendar year, this galaxy was already shining before the clock had even ticked past its first week. And here's where it gets genuinely strange. This galaxy is 100 times brighter than it should be at that age and distance. Not a little brighter, not slightly off our models, 100 times. That is not a rounding error. That is something our current understanding of early galaxy formation simply does not have a clean explanation for. But the brightness is almost the least surprising part. MOMZ14 also contains nitrogen, an element that requires hundreds of millions of years of stellar evolution to produce. Stars have to be born, burn through their fuel, explode as supernovae, seed the surrounding gas, and then an entirely new generation of stars has to form from that enriched material before nitrogen starts showing up in meaningful quantities. That process takes time, far more time than the universe had on the clock when this galaxy was already glowing. And yet the nitrogen is there, unmistakably written into the light. On top of that, MOMZ14 is sitting in a region of space that should still be filled with what cosmologists call the primordial fog, a dense, neutral hydrogen haze left over from the early universe that blocked light from traveling freely, an era known as the epoch of reionization. That fog was supposed to still be thick and pervasive at this point in cosmic history, but somehow, around this galaxy, it is not. Something cleared it. Something pumped out enough high-energy radiation to carve out a bubble of transparent space in the middle of what should have been an opaque universe. The scientists who found it have started calling it a cosmic miracle. That phrase sounds dramatic coming from researchers who usually deal in precise, cautious language. And that's exactly why it's worth paying attention to. Because the more you sit with the data, the more it feels like we are staring at something that our best models say shouldn't exist. Not yet, not there, not like this. Before we start, I want to tell you something. A lot of strange things have been happening in space lately, so subscribe to this channel right now, and I'll tell you even more secrets of space. And write in the comments below what you think about all of this. To understand why MOMZ14 is so unsettling, you need to understand what the early universe was supposed to look like. After the Big Bang, the universe was a hot, dense soup of particles. No stars, no galaxies, just hydrogen, helium, and a tiny bit of lithium expanding outward into nothing. For the first 100 million years or so, the cosmos was completely dark. Astronomers literally call this period the Dark Ages, and the name is apt. There was no light, no structure, no complexity of any kind, just a slowly cooling fog of matter drifting apart in the aftermath of creation. Then, somewhere around 100 to 200 million years after the Big Bang, the first stars finally ignited. These weren't stars like our sun. They were monsters, hundreds of times more massive, burning through their fuel at ridiculous speeds and dying in violent explosions that scattered heavier elements into space for the very first time. These early stellar giants, sometimes called population 3 stars, lived fast and died spectacularly, seeding the cosmos with the raw ingredients that would eventually make planets, chemistry, and life possible. But here's the thing. Those first stars were supposed to be rare, isolated, and struggling to form in a universe that was still mostly empty. The first galaxies, tiny, dim, and chaotic, more like small loose clusters of stars than anything we'd recognize today. That was the model. That was what decades of physics, computer simulations, and careful observations had led us to expect. Galaxies needed time to grow. They needed gravity to slowly pull gas clouds together, compress them, trigger star formation, and repeat that process across billions of years before anything resembling a mature, massive galaxy could exist. The universe had rules, and those rules took time to play out. But then the James Webb Space Telescope launched in December 2021, and within months of its starting science operations, astronomers started finding galaxies that had no business existing, galaxies that were too big, too bright, too mature, too early. Objects that seemed to have already packed in enormous amounts of stellar mass at a point in cosmic history when they simply shouldn't have had enough time to do so. At first, scientists thought maybe they were making measurement errors. Maybe the photometric data was misleading. Maybe these weren't actually distant galaxies at all, but nearby objects whose light had been reddened by dust, making them look further away than they really were. Dust can do that. It preferentially scatters shorter wavelengths of light, shifting the apparent color of an object toward the red end of the spectrum and mimicking the effect of cosmological redshift caused by the expansion of the universe. It's a known source of confusion, and it seemed like a reasonable explanation, so they designed a survey specifically to find out. They called it Mirage, or Miracle. The name captures the two possible outcomes perfectly. And MOMZ14, it turned out to be the biggest miracle of all. The Mirage, or Miracle survey, was led by Pascal Oesch from the University of Geneva and Rohan Naidu from MIT's Kavli Institute. Their goal was simple but crucial. Take all those suspiciously bright objects that JWST had been finding at extreme distances and confirm whether they were real, because if they were mirages, dusty nearby galaxies pretending to be ancient ones, then our models were safe and the universe was still behaving itself. But if they were miracles, genuine galaxies from the cosmic dawn, then something was seriously wrong with our understanding of how structure in the universe forms and evolves. On April 16, 2025, the team pointed JWST at one of these candidates and let the telescope stare for about 4.5 hours. They used NIRCam for imaging and NIRSpec in prism mode for spectroscopy, which basically means they collected enough light to break it apart into its component wavelengths and figure out exactly what chemical elements were present and in what abundances. Spectroscopy is the gold standard here. Photometric redshifts based on color alone can be fooled, but a spectrum gives you the actual fingerprint of the light, locking in the physics with far greater certainty. When the data came back, the redshift measurement was definitive. Z equals 14.44, plus or minus 0.02. No ambiguity, no error bars big enough to explain it away. This wasn't a mirage. MOMZ14 was sitting at a distance where its light had traveled 13.5 billion years to reach us. Due to the expansion of the universe, the galaxy is now roughly 33.8 billion light-years away, in what astronomers call co-moving distance, a measure that accounts for the stretching of space itself since that light first began its journey. But when we look at it, we're seeing it as it was when the universe was just 280 million years old. To put that in perspective, the universe today is approximately 13.8 billion years old, which means we're peering back at a time when the cosmos was barely 2% of its current age. The research team published their findings in a paper titled A Cosmic Miracle, a remarkably luminous galaxy at Z-spec equals 14.44, confirmed with JWST, 46 authors from institutions around the world, peer-reviewed, published in the Open Journal of Astrophysics. This wasn't speculation, this was confirmed. But confirmation was only the beginning, because the numbers that came out of that data were absolutely baffling. Z14 is roughly 100 times brighter than theoretical models predicted any galaxy could be at that epoch. These models weren't rough guesses. They were built on decades of observations, simulations, and carefully tested physics. And yet, the universe appears to have ignored them entirely. According to the survey data, the number density of bright galaxies at redshift 14 to 15 is somewhere between 77 and 511 times higher than what pre-JWST models expected. The best estimate sits around 182 times higher. Think about that for a second. We didn't find a few extra galaxies scattered where they shouldn't be. We found hundreds of times more than we thought was physically possible. This isn't a rounding error or a statistical fluke. It's a systematic, dramatic departure from everything our models told us we'd see. And the brightness isn't the only problem. There are 3 major issues with MOMZ14, and each one challenges something fundamental about how we thought the early universe worked. Problem 1. It's way too bright. MOMZ14 has an absolute UV magnitude of minus 20.2. That's an astronomical measurement of intrinsic luminosity, independent of how far away the object is. And for a galaxy this early in cosmic history, the number is genuinely absurd. The galaxy is only about 500 light-years across. For comparison, the Milky Way is roughly 100,000 light-years in diameter, making our galaxy a sprawling cosmic metropolis by comparison. MOMZ14 is about 400 times smaller than our galaxy, so compact that Harvard astrophysicist Avi Loeb described it as being 100 times smaller than the distance between our Sun and the center of the Milky Way. It's tiny, a dense, almost impossibly concentrated knot of matter in the early universe. But despite being tiny, it's packing roughly 100 million solar masses worth of stars into that compact space, a stellar density that strains our understanding of how efficiently the universe can convert raw gas into shining suns. And on top of that, it's undergoing a dramatic starburst event, with star formation rates that increased tenfold in just 5 million years before we observed it. In cosmic terms, 5 million years is almost nothing, a brief, violent surge of creation, happening at a speed our models struggle to account for. Standard models said galaxies this early should be dim, diffuse, and struggling to hold themselves together. MOM Z14 is compact, bright, and thriving. It joins only 2 other confirmed galaxies as what the researchers call extremely compact outliers at redshifts above 10. These galaxies shouldn't be this bright, at this size, this early in cosmic history. But as troubling as the brightness problem is, it turns out to be almost manageable compared to what comes next. Problem 2. The nitrogen mystery. When the near-spec instrument broke down MOM Z14's light into its component spectrum, it detected something that, by all rights, should be impossible. 5 distinct emission lines, including clear signatures of nitrogen, and not just trace amounts. The nitrogen-to-carbon ratio in this galaxy exceeds 1, which is substantially higher than what our own sun produces over its entire lifetime. Here's why that detail is so deeply unsettling. The universe in the immediate aftermath of the Big Bang contained only 3 elements: hydrogen at roughly 75%, helium at roughly 25%, and vanishingly small trace amounts of lithium. That was it. Every heavier element, from carbon to oxygen to nitrogen to iron, had to be painstakingly forged inside the cores of stars over vast stretches of time. Carbon forms through what's known as the triple alpha process, which occurs when stellar cores are compressed and heated to temperatures exceeding 100 million degrees. Nitrogen is considerably trickier. It primarily accumulates through the CNO cycle and reaches significant abundances mainly through the death of intermediate mass stars, specifically during what is called the asymptotic giant branch phase of stellar evolution, a slow and dramatic twilight stage that only certain stars ever reach. The timeline problem is brutal. Asymptotic giant branch stars in the 3 to 8 solar mass range require somewhere between 100 and 500 million years to evolve through their complete life cycles and finally disperse their nitrogen-enriched material back into the surrounding space. And even that isn't enough on its own. Multiple successive generations of stars have to live, burn through their fuel, and die in order to build up the kind of nitrogen enrichment we are actually seeing in MOM Z14. But here's the catch. MOM Z14 existed when the universe was only 280 million years old. The very first stars in the cosmos probably didn't even ignite until somewhere between 100 and 200 million years after the Big Bang. Do the math. That leaves, at most, maybe 80 to 180 million years for all of this chemical enrichment to have taken place. The stellar physics we understand says you simply cannot produce this much nitrogen in that kind of time frame. It's not a minor discrepancy, it's a fundamental contradiction. The lead researcher stated it plainly and without equivocation. The nitrogen spectral features observed in the early galaxy MOM Z14 cannot be produced by normal stars operating within 280 million years after the Big Bang. In response to this puzzle, the research team proposes that the extraordinarily dense and energetic conditions of the early universe may have given birth to what they describe as supermassive primordial stars, objects capable of producing nitrogen through physical mechanisms that are simply unavailable to any stars we observe in the local universe today. In other words, stars that no longer exist anywhere we can see, stars that operated under entirely different rules. Problem 3. The missing fog. There is one more anomaly layered on top of all of this, and it may be the strangest of the 3. At 280 million years after the Big Bang, the universe should have been saturated with neutral hydrogen gas. Astronomers refer to this pervasive, all-encompassing medium as the cosmic fog. It is the leftover hydrogen from the Big Bang that had not yet been stripped of its electrons and ionized by the intense ultraviolet radiation pouring out of early stars and galaxies. This fog didn't fully clear until what's called the epoch of reionization, a transformative period in cosmic history that wasn't completed until around 550 million years after the Big Bang. Before that threshold, neutral hydrogen should have been effectively everywhere, absorbing and scattering the light from early galaxies and rendering them far dimmer and more obscured than they would otherwise appear. At the moment Z14 existed, theoretical models predict a roughly 100% neutral hydrogen fraction in the intergalactic medium directly surrounding it, meaning the fog should have been essentially total and impenetrable. The cosmos should have been opaque at that epoch, yet the spectrum of MOM Z14 shows remarkably little evidence of this neutral hydrogen. The region surrounding it appears to be at least partially ionized already, which is deeply puzzling given how early in cosmic history we are looking. As astrophysicist Ethan Siegel asked in Big Think, how is there so little neutral gas present in this region so early on? Either MOMZ14 represents an unusually precocious bubble of ionization, a pocket of preternatural clarity punched through an otherwise foggy universe, or reionization happened much faster and far more unevenly than our models have ever assumed. Either way, something is genuinely wrong with our picture of the early cosmos, and the magnitude of that wrongness is still being reckoned with. Here is what makes MOMZ14 so significant. It is not an isolated anomaly, a one-off curiosity that astronomers can quietly set aside while the rest of their models hold firm. Ever since JWST began science operations in July 2022, astronomers have been finding these so-called impossible early galaxies over and over again, with a frequency that has gone from surprising to deeply unsettling. In fact, Rohan Naidu, one of the lead researchers on MOMZ14, was the very same scientist who flagged the first suspiciously massive object in JWST's early data just weeks after the telescope came online, a sign that the instrument was going to challenge assumptions from the very start. As one NASA summary colorfully put it, scientists had expected to find galactic pipsqueaks in the early universe, small and fragile infant structures still assembling themselves from the primordial dark, but instead discovered what appeared to be a bevy of Olympic bodybuilders, galaxies that were inexplicably large, bright, and mature for their age. The distance record has fallen repeatedly and with increasing speed. JADES-GS-Z13-0 held the title briefly at a redshift of 13.2, placing it among the earliest confirmed structures ever seen. Then in May 2024, JADES-GS-Z14-0 claimed the record at a redshift of 14.32. Existing roughly 290 million years after the Big Bang, and carrying an estimated mass equivalent to 500 million suns. When the ALMA Observatory refined that galaxy's data in early 2025, it also detected oxygen emission lines from it, representing the most distant observation of that element ever made, and implying that multiple generations of massive stars had already lived and died to produce it. Now MOMZ14 has pushed even further back into territory that should by all rights be structurally empty. The problem is not individual outliers, it is systematic excess, a pervasive and reproducible pattern that cannot be explained away by measurement error or bad luck. Studies document more than 10 times higher number densities of bright early galaxies than extrapolations from pre-JWST Hubble data ever predicted. A sample of 88 galaxies showed early systems at least an order of magnitude brighter than theoretical models had forecast. Stefano Carniani of the Scuola Normale Superiore called JADES-GS-Z14-0 the most distinctive evidence yet found for the rapid formation of large and massive galaxies in the early universe. And now we have MOMZ14 pushing even further into what should be impossible territory, demanding an explanation that our current frameworks are straining to provide. So what is actually going on? Initially, some scientists worried that JWST might be doing something far more dramatic than finding surprising galaxies. They worried it might be breaking the standard cosmological model itself, the lambda-CDM framework, that describes the large-scale structure and evolutionary history of the universe with remarkable precision across billions of years of cosmic time. That concern has mostly faded as the data have matured and been scrutinized more carefully. Stephen Finkelstein of the University of Texas at Austin summarized the emerging consensus with measured confidence. There is no crisis in terms of the standard model of cosmology, he argued. Anytime you have a theory that has stood the test of time for as long as lambda-CDM has, you have to have truly overwhelming evidence before you can seriously consider throwing it out. And that, he concluded, is simply not the case. What we may have instead is something more subtle and arguably more interesting, a set of missing ingredients, processes operating in the early universe that our models have underestimated or overlooked entirely. Work by Katherine Swarowski and colleagues in 2024 helped resolve some of the tension by identifying that many compact red objects, nicknamed little red dots, actually contain rapidly accreting black holes that inflate their apparent masses. When a black hole is feeding aggressively, the intense radiation it produces can mimic or amplify the signatures of stellar mass, making a galaxy appear far more massive than it truly is. Removing these contaminated objects from galaxy samples roughly halved the discrepancy with models, which was a meaningful step forward. But MOMZ14 can't be explained away that easily. Its spectrum is dominated by stellar emission, not black hole activity, meaning the extraordinary mass we're seeing appears to be genuinely locked up in stars. The leading explanation now involves dramatically higher star formation efficiency in the early universe. Standard models assume galaxies convert roughly 20% of available gas into stars, a figure calibrated against the galaxies we can observe in the relatively nearby universe. Early galaxies may have achieved 30% or even higher efficiency through what researchers call feedback-free starbursts, where the extreme density of the early universe prevented the normal processes that slow star formation down. In typical galaxies, the radiation and winds from newly born stars heat surrounding gas and suppress further collapse, acting like a natural brake on the system. In the dense, compact conditions of the very early universe, that brake may simply not have engaged. There are other proposed mechanisms as well. A top-heavy initial mass function could have skewed early stellar populations toward more massive, more luminous stars, making the same amount of stellar material shine far more brightly than we would expect. Reduced dust attenuation may have allowed more ultraviolet light to escape freely into space, again inflating observed brightness. Bursty star formation episodes could have made galaxies appear up to 10 times brighter during their most active phases, catching us at a particularly spectacular moment. But none of these fully explain the nitrogen. None of them explain the cleared surroundings. Each proposed solution addresses one corner of the puzzle while leaving the rest in disarray. Joel Leha of Penn State captured the situation with uncomfortable precision. "It's very confusing," he noted. "You can make this uncomfortably fit in our current model of the universe, but only if you invoke some exotic, insanely rapid formation at the very beginning of time." He added that we have all these puzzle pieces, and they only fit together if we ignore the fact that some of them are already breaking. So where does this leave us? MOMZ-14 is now the most distant confirmed object humanity has ever observed. Its light traveled 13.5 billion years to reach us, crossing nearly the entire history of the cosmos before arriving at a telescope that had existed for only a handful of years. We are looking at something that existed when the universe was barely beginning to wake up, when the first structures were still pulling themselves together out of primordial darkness. And it makes no sense, not in a casual way, not in a way that a small correction to the models can absorb. It makes no sense in a way that genuine discoveries rarely do, pointing somewhere we haven't been before. It's too bright. Its chemistry is wrong. Its surroundings are too clear. Every piece of data from this galaxy suggests that the cosmic dawn wasn't the gradual, orderly awakening the textbooks described. It was something more violent, more efficient, more strange, populated by stellar behemoths that may no longer exist anywhere in the observable universe, governed by processes that operated under conditions we've never directly seen and may never see again. These weren't stars in any sense we'd recognize from our own cosmic neighborhood. They were monsters, forged in an era when the raw ingredients of the universe, hydrogen, helium, and almost nothing else, collapsed under gravity into objects so massive and so luminous that they burned through their fuel in mere millions of years, living and dying before our own solar system had any right to even dream of existing. As Vicky Wilde commented in Sky and Telescope, it was frankly pretty naive of astronomers to have assumed star formation in the early universe would resemble later epochs. We've been looking at the universe as baby pictures and assuming babies act like adults. But infants don't think, move, or consume energy the way grown humans do. And it turns out infant galaxies don't behave the way mature ones do either. MOMZ-14 is telling us that cosmic infancy was wild in ways we're only beginning to understand, that the rulebook we've been using was written for a universe that had already calmed down, already aged, already lost much of its original ferocity. The James Webb Space Telescope will keep staring deeper, pushing its golden mirrors further back in time with every observation, collecting the ancient light of galaxies that existed when the universe was barely a few 100 million years old. Each new image is less a photograph and more a dispatch from an alien era, a reminder that the cosmos we inhabit today is just one chapter in a story that began under conditions almost incomprehensibly different from our own. More impossible galaxies will probably emerge, and each new discovery will force us to revise our understanding of how everything began. Graduate student Yijia Ali put it best when she said that, to figure out what is going on in the early universe, we really need more information. It is an incredibly exciting time, with the Webb telescope revealing the early universe like never before, and showing us just how much there still is to discover. The early universe wasn't just different from today, it was actively strange, almost unsettlingly so. It accomplished in mere millions of years what our best models said should have required billions, building massive, mature structures at a pace that seems to defy the very physics we rely on to describe the cosmos. And it did so through mechanisms that may have operated only during that singular, unrepeatable cosmic moment. Forces or conditions or feedback loops that flickered into existence, drove the formation of entire galaxies at breakneck speed, and then vanished forever, leaving behind no obvious trace except the galaxies themselves, hanging there in the deep field images like evidence of something we don't yet have the language to explain. That's not just fascinating, that's kind of creepy. It suggests the universe had a chapter in its early life that played by different rules that were later retired without warning, and that we are only now, through instruments of extraordinary sensitivity, pointed at the most distant corners of space and time, beginning to glimpse what those rules might have been. That's all for today. If you like space stories and want to stay up to date with new episodes, subscribe to this channel and turn on notifications. See you in the next podcast.